All right, folks, let's get to it. We have now introduced homeostasis, so we're going to look at the specific example of temperature regulation. Temperature regulation allows endotherms, those animals that we call warm-blooded, to be ready for movement at any time. So it has a very high evolutionary advantage. If you think about ectotherms, so reptiles, fish, those kind of things that are not so-called warm-blooded, ectotherms cannot internally regulate their body temperature. So all of the regulation they have to do is behavior based. They have to go out in the sun to get warm. They have to go in the water to get cool or underground to get cool and those types of things. They don't have any of the internal mechanisms that endotherms do to be able to handle that. So because there are still ectotherms, we got to imagine that evolutionarily, it must be okay. Some animals survive and reproduce just fine with that, but some selective pressures in some environments influenced endotherms to evolve instead. It is advantageous, but it's incredibly expensive from a biological viewpoint, meaning that to be running the heater all the time. So maybe let's imagine that an ectotherm is kind of like having a heating or cooling system in your home that is not run on a thermostat, like just a window unit. You have to manually choose to turn on and choose to turn off. And maybe it doesn't work quite as well. It only heats or cools when you're standing right in front of it. That's my experience with the window unit anyway. So let's imagine that's like an ectotherm's temperature regulation. It works, but doesn't work as well as something with a thermostat, like central heating and air, but you can save money that way. It's not quite as expensive because you're not going to be running heat or air all the time. You're just going to turn it on when you need it. And we see this in reptiles and fish. They don't have to eat as often as endotherms. If you've ever had a pet lizard or snake or something like that, they eat very infrequently compared to endotherms because they're not burning as much energy. They are choosing to go out in the sun and just passively get warmer, get under their little lamp, for example. Endotherms, on the other hand, are like having a central heating system with a thermostat, and we are constantly just radiating heat, just losing energy, constantly producing heat. If you've ever been pregnant and carried a term, I've heard a lot of pregnant people talk about their baby as feeling like a little heater right on top of all their organs. And humans certainly are. You notice this when you're around others. I mean, that's why you can sort of huddle for warmth, cuddle for body heat, and those types of things. But it's incredibly expensive to do that. You're running the heat 24/7. You're not just turning it on when you need it. It's always there. So it's very expensive. Endotherms have to be able to find and eat a whole lot more food, a whole lot more consistently than ectotherms do. So why did some animals even evolve this if it's so expensive? That's one question that biologists have attempted to answer. With ectotherms, there's a cost to them not constantly being warmed up at all times. Again, if you've had any reptiles as pets, you might notice that when they're cold, they're sluggish. They don't move around as much and they don't move as quickly. They have some energy stored in fast twitch muscles that allows them to run away very quickly, just for a short period of time if they are threatened, and they can move to safety. You know, lizards will kind of skitter under a rock or something like that. But they are not consistently warmed up for longer term movements. They're not able to really have any endurance exercise going on. Endotherms, on the other hand, are able to do that. So because we do have the heat on at all times, we've got the energy to be ready to move at any time. And we also have the energy to sustain that movement for a very long amount of time. So it's very expensive in that we have to eat a lot and we burn a lot of calories, but it's advantageous enough to outweigh that because it allows us to be more mobile more of the time. Small endotherms have a harder time with this. They have what seems to be a faster metabolism where they have to eat much more often because they have a surface area to volume ratio such that they are radiating too much heat for the size of their body. So birds, for example, you see having to eat a little bit just constantly all day long. Small mammals like mice or shrews can starve to death within just a few hours because their metabolisms are that fast. Because again, they have the heat cranked up constantly, but they have to feed that with fuel. It's sort of like having a fire burning all the time. And imagine having to feed it with firewood constantly. You could run out pretty quickly if you're running that heat constantly. Larger animals, on the other hand, they don't have as much skin relative to the size of the volume of their body compared to smaller animals, and so because of that, they're able to retain more of their heat relative to their body size. And they also tend to have layers of fat and to store their food as fat to help them have more energy to burn. So they can, instead of birds that tend to be more lean and have to just eat constantly all day, every day, and just keep enough firewood to put there in the fire, larger animals can store fat, which is like having kind of a backlog and a stock of firewood that you can pull from if you didn't get to go chop any that day. So we've talked some about temperature regulation when it comes to heating and why there's kind of a trade-off there, but we haven't really talked about cooling, mostly because being an endotherm, we call it warm-blooded because we're sort of constantly burning that fire to keep our body temperature up. We don't have quite as many mechanisms to cool down the body temperature. We mostly have sweating to cool us down. Humans are the land animal with the most endurance. So a well-trained human can run for longer, not faster, can run for longer than any other animal on land. And this is because of our superior cooling mechanism. Our closest contender for animals that can run endurance like that is the horse. And horses also sweat. Not all mammals do. So you're probably familiar with the fact that your dogs and cats don't sweat. They have to pant to try to radiate heat out of their bodies quickly, but they don't have a lot of other ways of cooling down. But humans sweat. Horses sweat. Sweat gives you that feeling of being cool as the water evaporates from your body, and it takes some of that body heat with it when it evaporates. So you have the fluid coming out onto your skin. It pulls some of the heat from your skin, so that water kind of warms up and then it evaporates into the air, and that pulls some of your heat away from your body. So sweating is annoying, and I know we live in a really hot climate where that's something we have to deal with from March through October for the most part, but it's actually a superior cooling mechanism that before air conditioning was probably one of the biggest factors that made humans so adaptable and able to live just about everywhere on the globe. Now, the reason we can outlast horses in long-term racing is that, as I said, horses do sweat, but they don't sweat in the same volume as humans. So we're sweatier, and that makes us better distance runners. But also, horses have fur all over their bodies, and humans with less of our body hair and with our adaptations of being able to create clothing that can wick away moisture even better and things like that, we are able to cool ourselves more efficiently. So humans especially beat out horses at endurance racing when the temperature is above 80 degrees Fahrenheit. Below that, it's a lot closer, or horses may win out, but above 80 degrees, well-trained humans can outrun even well-trained horses.